Nenad Pesma. In this video we will solve a trigonometric problem using Polya's how to solve it method. Here is the problem. The expression 3 sin x minus 5 cosine x can be written in the form r times sin x plus a, where r is positive and a is between 0 and 2 pi. Calculate the values of r and a. Let's begin with step 1, which is understanding the problem. The first question we should ask is, what is the unknown? Looking carefully at the problem formulation, we are looking for the words like determine, calculate, find, or similar. In our example, we have the word calculate. Calculate the values of r and a. So our unknown are those two quantities, r and a. The next question to ask is, what is given? We cannot solve a problem without being given something. So what is given? Looking at the problem formulation, we see the statement that a certain expression can be written in some other form. That means that those two expressions are equal. So we write 3 sin x minus 5 cosine x is equal to r times sin x plus a. Is anything more given? The problem formulation says that r must be positive and a must be between 0 and 2 pi. Let's write that down. Why is that required? That is because the equality of the two expressions here is not unique. We know that the sine function is odd and that it is periodic. That means that when we add pi to a minus sign falls out. And when we add 2 pi, we get the same value as before. But if we demand that r should be positive and that a is between 0 and 2 pi, then there will probably be unique values of r and a that satisfy the equation. Step number 2 is devising a plan. We have our equation from the previous board, and that will help us find r and a. We ask ourselves, have you seen it before? On the right-hand side, we see a sign of a sum of two angles, the angle x and the angle a. If we have studied trigonometry, we probably have seen it before. We ask ourselves, do you know a theorem or a formula that you could use? We have seen a formula where a sine of a sum of two angles is some expression involving sines and cosines, but we have forgotten how it looks. That should not scare us. Formulas that we have forgotten can almost always be retrieved with little guessing and sound reasoning. So our first goal should be to derive the formula for sin x plus a. Having done that step will enable us to express the right-hand side of this equation, so we then can identify the coefficient in front of sin x with 3 and the coefficient of the cosine x with minus 5. In other words, we will set up an equation system, and as the final step, we will calculate r and a by solving that equation system. That is our plan. Step number 3 is carrying out the plan. Here we must check that each step is correct. We want to derive the formula. We have some vague memory that it looks something like this. Sine sine plus cosine cosine. Or maybe a minus sign here. We can't remember. Or maybe like this. Sine cosine plus cosine sine. With a possible minus here. Something like that. But which one is it? Let us check. If we set beta equals 0, we get the following equation. That would mean that sine alpha equals cosine alpha, which is dead wrong. So this formula is incorrect, and we can cross it out. Let's test the next formula. If we set beta equals 0, we get the following equation. That would mean that sine alpha equals sine alpha, which is correct. So it seems that this formula is the one we are after. Let's check with some other value. If we set beta equals pi over 2, we get the following equation. That means that sine alpha plus pi over 2 is equal to cosine alpha. But that is correct, as we can see in the following figure. When we rotate a radius vector pi over 2 radians, or 90 degrees, the cosine alpha, which is the projection of the red vector on the x-axis, is equal to the projection of the blue vector on the y-axis, and that is sine alpha plus pi over 2. Hence, we conclude that this formula is correct. To customize this result to our problem, we set alpha equals x and beta equals a, which gives us the following equation. We have thus done the first point of our plan. Let's continue on a new board. We'll take this equation with us, and also the one we derived. As you can see, we have sine x plus a in both equations. So we can use this to put into the right-hand side of this equation here. Thus we get the following formula. We can identify the coefficients in front of sine x and cosine x and get the following two equations. 3 equals r times cosine a, and minus 5 equals r sine a. Two equations and two unknowns. We need to solve it. We can divide the two equations to get rid of r and then calculate a, and afterwards go back and calculate r. Another way is to use a little trick. We all know the following formula. Cosine squared plus sine squared equals 1. We can use that to square our two equations and get r squared equals 3 squared plus 5 squared, which is 34. Hence, r is square root of 34, and the calculator tells us that this is approximately 5.83. To get a, we divide equation 2 with equation 1 and get tangent a equals minus 5 divided by 3. Hence, a equals arctangent minus 5 over 3, and the calculator tells us that this is approximately minus 1.03. But this is not the value we are looking for. The problem said that a should be between 0 and 2 pi. Let's take a closer look at where our angle is. According to our two equations here, the cosine A is positive, while the sine A is negative. Let's write it here. And let's draw a coordinate system. In the first quadrant, both cosine and sine are positive, so our angle A is not there. In the next quadrant, cosine is negative, while sine is positive. Wrong again. In quadrant 3, both cosine and sine are negative, so wrong again. In the fourth quadrant, the cosine is positive, while sine is negative. That is correct. So our angle A is in this quadrant. And what the calculator says is that the angle is minus 103 radians, which is about minus 50 degrees. But we are after the positive angle, which is 360 minus 50, that is about 310 degrees, or 5.25 radians. So our angle is 2 pi minus 1.03, which is 5.25. At last we have calculated R and A. But we should not stop there. The last step, according to Polya, is looking back. The first question to ask is, can you check the result? Our result is 3 times sine x minus 5 times cosine x is approximately equal to 5.83 times sine x plus 5.25 radians. How can we check this result? This is supposed to be true for any x, so we can pick up a particular x and check. Let's try with x equals 0. The left-hand side becomes minus 5, and the calculator gives that right-hand side is minus 5.01. Close enough. Let's try another value. X equals pi over 2. The left-hand side becomes 3, and the calculator gives that the right-hand side is 2.98. Good enough. Another question we should ask is, can you derive the result differently? The main hurdle of solving the problem was to derive the formula for the sine of a sum of two angles. Let's derive it differently. This time we will use Euler's formula. We are interested in the following expression. We can write it in the following way. We have the formula for the first factor, and we can write the second factor as follows. According to Euler's formula, we can write the left-hand side of this equation as, and we can write the right-hand side as. By multiplying out the right-hand side, we can find the real part and the imaginary part, and equate it with the real part and the imaginary part of the equation on the left-hand side. The real part gives the formula for the cosine of sum of two angles, and the imaginary part gives the formula for the sine of the sum of two angles. And as you remember, this is the same formula that we derived earlier. We have reached the end. You've been watching a video by Nenad Pesma.